Hey everyone, so once again, for tonight's video, we're gonna just sort of treat it like we're in class and going through class using our normal routines. So what I'd like for you to do is take a few minutes trying out the do now on the front on your own, and then pause the video obviously while you're working on the do now, and then when you're done you can restart the video and check your answers. So for the first problem in the do now, a kindergarten class is lining up to go to gym. There are 20 students. How many different ways can the class line up? You do not need to simplify your answer. So in this one, we're talking about a kindergarten class, a group of 20 different students that are lining up to go to gym. We know that when we have 20 different objects, or in this case people, lining up in a row, the number of different ways they can line up is given by 20 factorial. Now, when it says you do not need to simplify your answer, that means that you can just leave your answer as 20 factorial rather than giving like a single numerical answer. I'll write that when the answer is like so big that your calculator would have to put it in like scientific notation. So whenever it says you do not need to simplify your answer, you can just sort of leave your answer in terms of factorials. So the next problem says, the same class sits in a circle for reading time. How many different seating arrangements are there? Again, you do not need to simplify your answer. So for an arrangement of a group of different objects in a circle, and we're talking about 20 students again, we're going to take 20 factorial, and we're going to divide by 20. So remember, dividing by 20 when you're talking about a circular arrangement, it sort of gets rid of those extra arrangements that this calculation counts that aren't really different because they're just rotations of each other. So that's why we divide by the 20. And again, where it says you do not need to simplify your answer, that just means you can leave your answer like this and you don't need to get like a single numerical answer. So in the next problem, you have a big family dinner coming up, and there will be a total of 15 people there. You take a big stack of plates out of the cabinet, including 6 red, 4 yellow, and 5 white. And the question is, how many different ways can the plates be stacked up? So first, let's see how many there are in total. So there's a total of 15. So this is one of those situations where they're being stacked up, like they're being stacked on top of each other. So that's like being stacked up in a line, or it's not really a row because it's like a vertical row, but some kind of like a line, a linear kind of an arrangement. So we know that when we're talking about a linear sort of arrangement, we know that we're going to sort of start out with 15 factorial. And then we just have to divide if we have repetition. So here we have 6 red plates, so we have to divide by 6 factorial. We have 4 yellow plates, so we have to divide by 4 factorial. And we have 5 white plates, so we have to divide by, 5 factorial. Now again, when you put this into your calculator, you want to type in the 15 factorial divided by, and then this part in parentheses in the bottom. So let's see what we get by doing that. So we get 630,630. So let's try one last one. So your family decides to get a nice centerpiece for the table. The centerpiece has small floral plants in a row. There are 4 red, 3 yellow, and 2 orange. How many different arrangements of flowers are there? So let's see, so there are 4 red plants, 3 yellow, and 2 orange. So that makes a total of 9. So again, there are 9 objects being arranged in a row. So we start off with 9 factorial arrangements. And then what we have to divide by is we have to divide by some other factorials to sort of get rid of the repetition that this number calculates by treating each of the 4 red plants as if they actually look different. So we're going to divide by 4 factorial, 3 factorial, and 2 factorial. And if you plug that into your calculator, you should get 1260, I think. So there are 1260 ways of organizing those floral arrangements. So for the past few days, we've been working on finding the number of different ways that you can arrange an entire group of objects. So you take the entire group and you want to rearrange them. And the question is, how many different ways there are of arranging them? Today we're going to focus on a different question. So today we're going to focus on how many ways can we choose some subset of objects from a larger group. So we don't want to rearrange the entire group. We want to take the group, pick out a couple of them. So as one example, suppose that out of a class of 20, a teacher wants to choose 2 to go on an errand for her. How many ways could she do that? So that's one example of the kinds of question that you'll be able to answer after this video. So we're going to do 2 sort of sets of examples together. The first set of examples is going to be choosing objects from a group where order matters. And what I mean by order matters is that if you choose the same 2 things out of the group, the order that you pick them in actually matters. So let's look at a couple of concrete examples. So there are 20 students who run for class office. First, the president is elected, then the vice president, then the treasurer, then the secretary. The question is, how many different groups of class officers can be created? So, imagine we take the entire 20 students and we first elect the president. Well, how many ways are there of picking the president? Well, there are 20, since there are 20 students who are running for class office. Now, once the president is elected, then we have to elect a vice president. So for each of the 20 possibilities for who is president, there are going to be 19 different possibilities for who is vice president. So there's 20 different possibilities for who's president, and for each of those, there's 19 possibilities of who's vice president. So in total, between president and vice president, so far we're up to 20 times 19 different combinations. Now once the vice president is selected, there are 18 people left to be treasurer. And once the treasurer is elected, there are 17 people left to be secretary. And so if we multiply all these numbers together, that's going to tell us how many different ways we can elect a president, vice president, treasurer, and secretary. So let's multiply those out. So I got 116,280. So let's try another example. So in problem 4, it says you have 50 songs on your phone and decide to make a playlist of 6 songs to listen to as you go to and from school. You always listen to your playlists straight through, so the order of the songs matters to you. How many different playlists can you make? So we want to, out of 50, we want to pick 6 songs. So for the first song in our playlist, we have 50 choices. Then for each of those 50 choices for our first song, there are 49 choices for our second song. So up until this point, we have a total of whatever 50 times 49 is possibilities for the first 2 songs. That leaves 48 choices for the third song, 47 choices for the fourth song, 46 for the fifth, and 45 for the sixth. So let's see what we have in total. So in total, this is a number so big that your calculator is putting it into scientific notation. So I should have said that you didn't have to simplify. So I should have put that in the directions that you don't need to simplify, because this number is so big that your calculator puts it into scientific notation. So this one you could just leave like this. Now, let's look at some slightly different examples. So here's a different kind of problem. So instead of there are 20 students who run for office, and first we pick a president, then vice president, then treasurer, and so on. Let's look at a different kind of problem. So in this problem it says, again, there are 20 students who run for class office. Rather than electing separate positions, a group of 4 class officers is elected and they share all the responsibilities of the 4 normal positions. How many different groups of class officers can be created? So we're going to start in the exact same way that we did up here. So we're going to start out by saying, well, there's 20 ways of picking the first class officer. Once we pick the first class officer, there's 19 ways of picking the second, 18 ways of picking the third, and 17 ways of picking the fourth. So we're going to start out this problem very similarly to what we did before. But let's think a little bit about what's different about this problem than the previous problem. So let's pick 4 people to pick on. So let's say that, let's say that Alana or Jonah and Matt are our 4 class officers who are elected. So this is one possible group of class officers. Here's the problem. When we do this calculation, it treats it as being different if Matt was elected first, then Jonah, then Alana. It treats these 2 orderings as being different. If Alana is picked first, then Jonah, then Matt, it's treated as being different than if Matt was elected first, then Jonah, then Alana. But should we really treat these 2 groups as being different? We shouldn't, right? Because in this particular problem, it says rather than electing separate positions, a group of 4 class officers is elected, and they share all the responsibilities of the 4 normal positions. So the order that people are picked out of the group for this problem does not matter. For the previous problem, the order that students were picked out of the group does matter, because if it was that the first person elected was president, this group would mean Alana's president, is vice president, Jonah is treasurer, and Matt is secretary. Whereas for this arrangement, it would mean that Matt is president, Jonah is vice president, is treasurer, and Alana is secretary. So that's 2 very different groups of class officers. There are different presidents, there are different vice presidents. So for the problem where the order that people were elected mattered, where they got different roles based on when they were elected, that order mattered, and these 2 groups should be considered different. However, for this problem, these 2 groups should not be considered any different, and any arrangement of these 4 people should not be different at all. Like it shouldn't count as being different, because they're just going to all share the responsibilities anyway. So order doesn't matter. But this calculation treats these 2 groups as being different, and in fact, any way that we could jumble up these 4 names, this calculation treats as being 2 different groups. So again, we're going to have to divide by something to deal with that. So let's think about, for a particular group of 4 people, how many different ways are there of ordering those 4 names? Well, there's 4 ways of picking the first name, 3 ways of picking the second name, 2 ways of picking the third name, and 1 way of picking the fourth name. So there's 4 factorial, 4 times 3 times 2 times 1, different ways of ordering these 4 names. And 4 factorial, by the way, is 24. So there are actually 24 different ways that we could write out this list of this exact same 4 students. This calculation treats those 24 groups as being different, but really they're basically the same. In this problem, those 24 groups are basically the same. In the previous problem, where people ran for different offices and the first person elected was president, then VP, then treasurer, and so on, their order mattered. And so those 24 different groups that have these same 4 people should be treated as different. But in this problem, those 24 groups that have the same 4 people shouldn't be treated as different because they have the same responsibilities. And so there are all these groups of 24 that contain all the same names. But we only want to count, from each of those groups, we only want to count one of them. And so we're going to divide by 4 factorial, which is where we got 24 in the first place. So then we want to calculate this. And we get 4,845. So let's do another example together. So in example 6, it says, your sister also makes a playlist of 6 songs out of the 50 she has to listen to on the ride to and from school. However, she always listens to her playlists on shuffle, so any 2 playlists with the same songs are essentially the same to her, no matter what the order. How many different playlists can she make? So this is very similar to problem number 4 up here, where you have 50 songs on your phone and you have to pick 6 of them to make a playlist. And so we're going to start out in the same way that we did before. There are 50 possibilities for choosing the first song. Then for each of those 50, there's 49 possibilities for choosing the second song. Then for each of those so far, there's 48 possibilities for choosing the third song, and so on and so forth. So we stop once we have 1, 2, 3, 4, 5, 6 songs. However, if she listens to playlists on shuffle, if 2 playlists have the same 6 songs in 2 different orders, the 2 playlists aren't going to be any different to her, right? Because they're just going to be on shuffle anyway. So those 2 playlists, as long as they have the same 6 songs, they're basically going to be the same to her, because she always listens to them on shuffle. So 2 playlists that have the same 6 songs, we don't want to count as being different, but this calculation does count them as being different. So we have to think about, given a particular playlist of 6 songs, how many ways are there, how many different playlists that have those same 6 songs just in different orders? And the answer to that is 6 factorial. And so there are all these groups of playlists that all have the exact same song. But we only want to count one out of each of those groups. And so what we want to do is we want to divide by 6 factorial. So then we can plug this into our calculator, and let me see if it's such a big number that it gives you scientific notation. Nope, so this does end up being a big number, but you can write it down. So you end up getting this number here. So 15,890,700. So that's how many different playlists she has. Okay. What I would like for you to do, is pause the video and try out these problems here on your own based on what we've done in the past few examples. So pause the video now, and then after you finish them up, you can unpause, and then I'm just going to write down the answers quickly so that you can check your answers. So I'm just going to very quickly tell you the answers to these problems. So this first one is about a 3-number locker combination. So there's 3 numbers in the locker combination. Each of the 3 numbers are between 0 and 39. A number isn't used more than once within a single combination. And we want to know how many possible locker combinations there are. So for a locker combination, the order of the numbers definitely matters. So if you have the right 3 numbers, but you mix up the order, the locker will not open. So order definitely matters. So there are 40 different numbers to choose from for the first number, and then 39 for the second, and 38 for the third. And so in total, that gives us 59,280. And notice that we don't have to like divide by anything because the order does matter in these locker combinations. So we shouldn't divide by some factorial to sort of get rid of those extra copies of when there are sort of the same numbers in a group, but the order doesn't matter. So for the second problem, we're talking about lottery tickets. So suppose that on a lottery ticket you're picking 6 numbers from 1 to 50. I didn't write this in the problem, but suppose that you can't use the same number more than once. So then there's 50 possibilities for the first number, 49 for the next, 48 for the next, 47 for the next, then 46, and 45. But in these problems, the order does not matter. As long as you have the correct 6 numbers in any order, you're going to win. So you want to divide by 6 factorial, since the order doesn't matter. And this one said you didn't need to simplify your answer, so you don't have to simplify. So in number 9, I'm doing a computer lab, and I need to choose 3 students out of her class of 25 to go get the laptop cart. How many different ways can I pick 3 students? So there's 25 ways of picking the first student, 24 ways of picking the next student, and 23 ways of picking the third student. The order doesn't matter. If I pick Alice, then Jess, then John, that's not going to be any different if I pick John, then Alice, then Jess. And so the order doesn't matter. It's still going to be the same group of 3 students who are going to get the laptop cart. So we want to divide by 3 factorial. And we get a total of 2,300. Now in the next problem, I'm picking 3 students out of a class of 25 to do some errands. The first student goes and gets some markers, the second student gets some photocopies, and the third student brings a note to the dean's secretary. And so the question is, how many different ways are there of choosing students for these tasks? So there's 25 ways of picking the first student. Then once I pick the first student, there's only 24 options for the second student. And once I pick that student, there's only 23 options for the third student. The order does matter in this case because depending on what order I pick the students in, they're going to do different tasks. So picking John, then Alice, then Jess is going to yield different sets of tasks than if I picked Jess, then Alice, then John. So since the order matters, I'm not going to divide by any factorials, and I get 13,800. So, if you have any further questions on this topic, I would recommend going back and listening to any parts that you're still not sure about. Remember that the other video that I made is still up on the website, so you can also rewatch that one if you're feeling like the different kinds of problems are starting to get fuzzy for you. Tomorrow during class, you're going to do some mixed practice, and then Friday during class, I'll be back and you'll have the opportunity to ask me some questions. So make sure that you feel comfortable with everything that's been in the past 2 videos so that tomorrow when you get into class and need to do some mixed practice, you'll be able to do so well. And make sure that you bring this packet back to class because you'll need it for classwork. So good luck with everything tomorrow, and I will see you on Friday.